有点一过。
哎，
这个第5题，哦，它到底是这个层 identity 等于这个层 P 等于 identity？
对啊，你如果 reduce 是怎么 reduce 法？作用在谁？
作用在 P 身上，
对呀，
我拿到 I。
对啊。
哦，所以这个层 P 等于 I 啊。
对，这边的乘法是从这边开始，不是越靠近它的先做。
是 OK。看写OK。是我们的。
是1到1K 吗？
写倒反了。
也倒反了，这边也倒反了呗。
这里没有吧 ？inverse 没有，因为我这里乘10000，它这里乘10000嘛，这里乘等于走，所以它的10000的不是这样。
哦，是。
那如果我再把它 inverse，就是 P 等于的话，我是 1K 写前面。就是等于它如果没有 inverse，你懂哎？
谁写谁？现在写谁？
就是你最后不是要拿到 E 等于
哦，他们就是一些 transposition 啊。
像我这讲这个，它等于这个，我讲它的 inverse of transposition，对，就是 transposition，所以这个 P 它还是 transposition。对
product of transposition，
它还是一个 product。
啊，你是讲某个一是吗？
没有，它应该是问，
就是要 inverse 了过后还是 inverse 还是 transposition 吗？它就算有 inverse 在上面，它还是一个 transposition 啊。可能一定不，哎，可以，这个情况可以，那为什么他们真的是等于？因为 transposition 的 inverse 是他自己，
好的，
因为他的 transposition 的 inverse 是他自己才可以这样做。平时的话不一定。对，
这个是你的。
免了。
这个记得 PK 在最前面啊。
像我这边就要被人到。
那这边要死
哎，啊，你的标它是反的。
因为他前面就打针。我操！我操！那个我现在是你没死他了，我现在。好像告诉你了，没有。
你的交叉的条件多元。然后他问我全部的 epsilon， 每一个 epsilon 都确的了。它会变，它会变，delta 会变，它不是一个 delta 问我全部 epsilon， 每一个 epsilon 配一个 delta。哎，不是。看起来都奇怪。
老师，那让你吃。
有点奇怪。对哦，我们来要吃完它，它掉进去。
可以吃啊，这个肉好错了。
可以吃哦。它是米做的。
那不好吃啊。
不是，问题是我吸一吸它就软掉，不是？也不是哦，它就可吃，我不吃掉。它吸一吸就软了，我吃掉。 可以啊，真的去怎么干啊？
你要不要做
Hello, testing. Okay, so let's some of you come to my office hour yesterday and then ask you to produce a counterexample for this case here. So how should you read this logically? So let's write this down. I mean, how I interpret this. So I interpret this as a two sentence here. Okay, actually it's one sentence, but let's go through my logic first. Okay, so my logic was prove that a union of two subgroup of G is not a subgroup of G. It's generally not a subgroup of G unless you have this special condition on the subgroup, then the union is a subgroup. Okay, so I view this as a two part. Okay, obviously you can view as one part because unless you can turn it to a if then statement, right? But let's see my logic first. So actually this question, right, is logically equivalent to you take for all group G, okay, and then you take all subgroup, let's say H K G, then H union K is a subgroup of G, but you take the negation. Okay, so this is the first part. Okay, what's the second part? Second part was if what? If H is in K or K is in H, then H union the subgroup of G. Okay, and then I said that if you negate the first part here, right, you just need to give a counterexample. Okay, but you also can produce a proof for this. Okay, when I say proof, that proof is word for a specific case. Okay, if you imagine this proof, right, you need to consider some point that is in H but not in K, and then in K and not in H, and then you produce that proof that you won't have a subgroup here. But not that when you do this, right, you are assuming you have such subgroup already. Okay, so can you produce a subgroup? I mean, produce a group for first of all, produce a group, and then give me two subgroups that you can have point in H but not in K but not in H. So meaning this H and K should both be a proper subgroup. Only then you can do it. Then you can use your proof to prove that the union of those two subgroups is not a group. Otherwise, you just take two subgroups and then show me they don't satisfy either closure, either one. Identity for sure they have to satisfy because both of them subgroup. Maybe they don't contain some inverses. Obviously, I think they contain inverses because both of them. So the only thing need to violate is closure. So the union of two groups. Subgroup. Okay. And then I think the second part is easier because if one contains the other, what's the union? Union should be the larger one. But both of them are by definition subgroup. Does it make sense? Okay. If you want to provide a proof, that proof actually is quite restricted. You only restrict to a specific kind of subgroup, which are proper subgroups. Different proper subgroup in your original group. Okay. If you don't provide a proof, then you just come up with a counterexample. Does it make sense? So I mean, whenever we prove things, right, you should be able to write it in this kind of logical notation. Because why we love this kind of logical notation
it will be very clear for you if you want to do some negation. You know how to do negation of a statement or not? So if you see there's a quantifier, and statement here. So when you do negation, what do? You should turn the universal quantifier to existential. Universal to existential. And then statement, just negate the statement. Okay, so what's the statement is the union of hash union K is G. So if you negate this, become the union of hash union K is not G. Not separate G, sorry. Okay. Okay, now. So once you put everything into this kind of quantifier statement, then it's easier for you to do negation. And easy for you to see what you have to do. Does it make sense? In particular, this is very important for your MA. Right or not? Your MA has a lot of conditions. For epsilon, you need to find delta. Or if you change the existential and for all universal, then the statement change again. It's different meaning. Right or not? Did you learn in discrete math or not? If you swap existential and universal quantifier, it will give a different statement. Okay, so you need to be very, very, very careful. Okay. And then having this kind of statement and proving this kind of statement is different. Although they look the same, they look the same. If you assume this, what can you do? If you want to prove this, what you have to do. So it's very important. Okay, so when you learn pure maths, right, the one very important thing is to know what you have and what you want to do. These two things you need to separate. Okay, so if you want to make a good practice, good habit, okay, whenever you look at the question, maybe make two column table. Okay, one column say assumption, the other column say what's your goal, what's your target, what do you want to do, and then this will be very clear what you have and then what you need to achieve. Okay, otherwise you will just confuse, don't know which one you have, don't know which one I already got or what I want to prove. Does it make sense or not? Does it make sense? Okay, so in your mind, you should know what you have and then what you want to do. This is not for maths only, this is for your life also. Understand or not? Make your life clear. Okay, what you have, what you want to do every day. Okay? So, are you guys ready to submit your assignment tomorrow? No? What? So certain, no. Okay, it's okay. Certain is good. Okay. So when you want to submit? Next Wednesday. Next Wednesday, Next Wednesday, okay. Okay, we still have 2 office hours if you want to come. But okay, I can extend your deadline, but I'm gonna release the 3rd assignment tomorrow also. Okay, you should start and look at it at the same time. Okay, and then see what you need, and then maybe read those related stuff first. And then in class, when I teach to that section you don't understand, you can quickly ask. Does it make sense or not? Okay, I released earlier. Another thing I think we need to settle now also. How about exam on week 8 Thursday? Week 8, 2个了啊，其他人呢 ？Others also have 2 exams that week, is it? Week 8. What do you think? What's the date? Week 8, what's the date? What's the date? 9th of November. What the other things? Week 8. Which one? Week 8 Thursday. No. 7. Yeah? Change venue. Oh, right. Okay, I can do that. I think I will book 2 venues also, 2 classrooms, so that we can have enough space. How about, what do you think? What do you guys think at week 8? Hansing said cannot afford. What the others think? Cannot afford. Media also cannot afford. One can afford. Two big one. Okay. How about the rest? Cannot. Week 9, eh? Week 9 can. Okay, so if we're gonna do week 9, we're gonna substitute, meaning we need to push our assignment 4 forward. What we know? It's the same timing. It's like 2 weeks, 2 weeks, 2 weeks. Because the 8 week I put assignment test right, so assignment go to 9. So if we swap, then we just swap the 9 week to the 8 week. So we still have the two weeks assignment thing going on. Does it make sense? Oh, that one is delay. That one is delay. That one delay. We don't count delay. We count delay. We don't count delay. Okay. Yeah. So it's like we still have 2 weeks, 2 weeks. So we swap assignment 4 forward. Then we change midterm backward because you want more time to do revision, right? So I move backward. We can also do revision class before the midterm if you want. We can discuss again that one. That one later we can discuss. But we need to fix that first so that I can go book room or prepare my paper. Okay, so week 9, and then week 8 do assignment 4. Okay, around there will be the deadline for assignment. Okay, is it okay? The back okay or not? Okay, okay. So mark your calendar. So hopefully we can change venue. I will ask. Week 9 midterm. Okay, week 8 assignment 4. Okay. So for the scope, I think we will depend on our pace. I think I'll release maybe around week 6, 7 or what. I'll tell you where we take exam until which part. Okay, we'll decide. Yeah, I'll make announcement also. So basically, it's week 9 midterm. And we can also discuss about revision class if required later. Okay. Right, so let's start. Right, so recall some property we proved last time before we go into group homomorphism. So what we have introduced for the past 3 weeks, the main object we encounter is called groups. Well, groups is really, really important. And typically this group is non-abelian group. Okay? Typically it's non-abelian group. Okay, although the number you encounter always commute, no matter what order you add, is the same. But typically it's non-abelian. For example, what is a non-abelian group? Sn, the symmetric group. What is the symmetric group? Set of or commutation of n indexes. Why is it not non-abelian? Because it's a function composition. Function composition typically is not commutative. Okay, but that time we prove a theorem, right? If you look at the cyclic subgroup inside any group, right, it should be abelian. Okay, which is nice. Okay, this is really nice, right? You started with a non-abelian composition, but you found a subgroup that has a commutative LOC. This is very special, you know, 很神奇哦. In a cyclic subgroup, you still compose with these non-commutative LOC, but turn out that it is commutative. You should convince yourself, go to the S3, S4, S5, find a cyclic subgroup, and then go and check whether the composition is commutative or not. Okay, and then convince yourself. Actually, we prove it, but still an example will help you to understand the proof. So this means what? This means what? If you continue to take cyclic subgroup, it will always be abelian. Okay. So if you keep taking cyclic subgroup again, then it will be abelian again. Okay or not? Okay. So this is a nice thing about cyclic subgroup. So we have one notation. So if if X in G has order n, then the cyclic subgroup generated by X will denote as C and cyclic subgroup. Okay. Or maybe we should we do this now? Should we do it in more generality? So let me think. I shouldn't take any G. So let's say it like this. So it's a finite group. Okay. Remember we proved this statement or not? If X has an order n, what's the set containing the integer power of X reduced to what? The set containing 1, X, and then what? So wait. So what's this set here? We reduce it to 1, X squared up to X minus X to the n minus 1. Okay, so this n here refer to the order, also refer to the cardinality of this set. Does it make sense? Yeah, this is what we have proven last time. Okay, so I introduced this notation here. Okay, we call this group Cn. C because cyclic. N tells you the order. Okay. Yeah. So I just introduced this piece of notation. If you see it anywhere else. Right. So another thing we left last time was a group homomorphism. So a group homomorphism is what? It's a map. Right? It's a map between two groups. Okay, such that what? This is a very important property about this group homomorphisms here. Okay, such that if you take any two groups element from the domain, and first you multiply them, right or not? And then you apply phi. So it goes to the codomain already. Okay. The other thing you can do is you first apply phi on X and Y, then you multiply them together. And we require that these two operations equal. Okay. So if this is satisfied, then you have a group homomorphism. Okay. Okay, so this is a very important property for a group homomorphism. The only property you need to satisfy. Okay, and then I will show you today. With this property, we can have deduce much more nice thing about this map here. Any questions so far? Please keep this definition in your mind. We will keep using this. Phi xy equals to phi x times phi y. That's all. Okay. Right. So let's prove some property about a group homomorphism. So let's see. Be a map between two groups. First thing is, if you take a bunch of elements inside your domain, okay. So what do you want to do if we take a bunch of elements here? This is a group, right? So the only few things we're interested is look at their products. Here we want to put things together because it's a group. I don't know. Does it make sense? We want to put things together. So if you first take product of all of them, okay, and then you send it across, is it true that you can send them one by one and then multiply them together? Okay, so this is the first thing we want to prove. The second thing was this phi will maps identity in G to identity in G prime. Okay, this phi is behave very well. So we will send the identity in G in the domain to the identity in the codomain. Okay.
The other thing that this phi behave well is it will send inverses, two inverses. So these two inverses live in different world, right? Okay. So meaning what? So it means that if I have phi on some inverses, is the same as inverse of phi A. Okay, so meaning what? Meaning is like you can take the inverse out. It's like the inverse operation commute with your function. Then you can simply take the inverse out from the function. I don't know. So far, any question about the three statement? Is it clear? What is it doing? Okay. So now let's prove all of them. Okay, let's prove all of them. So A. So does A seems familiar or not? Does A seems familiar? Why is it familiar? Enchun ha. Enchun ha. Why? How familiar? Familiar to what? Similar to what? Yeah, something right just now. What did we say about group homomorphism? Yeah, so meaning what? For k equals to 2, we know that it is true. Okay. K equals to 1, there's nothing to prove, right? Vx1 equals to Vx1. Obviously, yeah. Okay. But if k equals to 2, this is what the homomorphism is. Okay. If k equals to 2, Vx1 x2 equals to Vx1 times Vx2 since what? Since phi is a homomorphism. Okay. I just put homo. Okay, so how to show for general K? What do you think? Yes, good. Induction. Okay, induction. So inductive hypothesis says what? Suppose it is true for K equal to K. K equal to N. Okay. Suppose that it's true for K equals to N. We want to show that it is true for, to show that the statement is true for K equals to N plus 1. Right. So let's look at what is the N plus 1 case. So consider what? Consider phi of x1, x2, dot until xk times xk. So how are we gonna use inductive hypothesis? So if we're gonna use, shouldn't be k, right? It is better to write n plus 1. So how to use the k equals to n statement? So we need to first reduce the number of elements inside here to n. So how? Do you see some bug here? Any bug? Bring up. No. Any bug or not? Did you notice that I didn't put any smaller bracket inside? But for LOC, you only know how to multiply two things. But so many things how to multiply. As a whole, sure, you can take it as a whole, but I mean, you still need to have like 2 by 2 products, right? Okay, if you take S1 to Sn2 as a whole, but how about inside one? Does it matter? Why not? Huh? Because what if I do the other way of combination? Does it really matter or not? Does it really matter how I group 2 by 2 together? Why not? Why not? Yes, because it is associative. But still there's a bug here. Associative only work for 3 elements. So you need to do induction for general n that is greater than 3.
Remember, I left an exercise, asked you to do for n equals to 4. It is still associative up to 4 elements if you assume associative on 3 elements. And then you can do it for 5, 6, 7, 8, 9, 10, and so on. Okay. If you are not sure, you should try and write it out yourself. Okay. So we can group them as we like because this is group. Okay, it's associative. Okay. So how should we group them? We can consider the grouping as follow. So we can group, for example, the first n term with what? Sn plus 1 here. Okay. After this, what can we do? So here I just simply write by associativity. So what happened next? Are we ready to use inductive hypothesis or not? Not quite though. Not quite. But what did you do? You somehow split it into a product of 2 group elements here. Isn't it this a base case? This is actually a base case. We're not yet using inductive hypothesis, but this is a base case because you have this whole bracket of element times 1 bracket of element. So this is a 2 group elements multiplied together. So this is a base case. So by base case, this can split into phi of x1, x2, and phi of Sn. Okay. Since let me write a little bit clearer. Since what? Since x1 dot x2 dot until Sn is still in G. Then what? So phi of n product of elements already. This is the inductive hypothesis. So by inductive hypothesis, we can split n product of elements. Okay, so by inductive hypothesis, we can write this as phi x1, phi x2, and so on until phi xn. Phi xn plus 1. And inductive hypothesis. Okay, so this is what we want. Okay, so we are done. So we are done. Does it make sense? Is it okay? Any question? Okay, as I found some of you are still not very familiar with inductive proof. So make sure you know how to do inductive proof and then how inductive proof work. Do you know how inductive proof work or not? Do you know? Yifang, is it Yifang? Can you explain how inductive proof work? So let's say I already done all these steps, right? How do I apply such that, for example, I have x1 to x100. Okay, how to say that I can split the product of x1 to x100 into this form?
xk is fine.
Okay, let's say my k is 100 now. How to say that it works for k equal to 100? How to apply? So you need to make sure that k99 is k equals 99 is true first. But how do you know k99 is true? You need to induct for me now. You need to induct for me. So how I make sure 99 is true now? How do I know 99 is true? Okay, let's go back faster, quicker. Okay, until 2 already. How do you make sure k equals 2 is true? No, I mean, okay, you said 97 has to be true, right? Then 96 has to be true, right? 95 needs to be true, right? So fast forward until k equals to 9. How do you make sure that k equals to 9 is true? Oh, sorry, k equals to 2. How do you measure? So you need to check the base case. You need to start from somewhere. So that's why our inductive proof must start with base case. Okay, not? Okay. So very important, 3 steps you need to remember in your inductive proof. First is base case. Second, inductive hypothesis. Third is inductive step. Okay, not? So only the first and the third step require proof. Okay, and then the third step require the inductive hypothesis to prove. If it turns out, so there's something to check here. If it turns out that the inductive step is not using inductive hypothesis, meaning what? If you can prove the inductive step without inductive hypothesis means what? Actually, you don't need induction already. Okay. Yeah, if you're gonna use induction, make sure you have to involve the inductive hypothesis. Yeah, inductive. Okay. Okay, so continue. Very important, inductive proof. So next, B, what do we want to show? We want to show that you send the identity in the codomain to the identity of the, domain to the codomain. Okay, so how are we going to prove this? So there's one technique I'm going to teach you, very important in mathematics. It's called 无中生有. Okay, you want 三国志吗? 三国志. Okay, 无中生有. So 无中生有 says what? You need to create something from nothing. Okay, so how do you create something from nothing here? This is a very good good property of identity. Why? Identity is equal to what? Identity times identity. So you can create an extra stuff here. Okay, so note that. So I want to prove two things are equal, right? So let's start with one side. So let's start with phi of 1g. So what is phi of 1g here? Phi of 1g here is phi of 1g times 1g. Okay, so what can you do here? Phi is a group homomorphism. Tell me what you can do here. I create a product for you already. This is equal to what? Phi of 1g times phi of 1g. Because this is a group homomorphism. This is a homo. Okay? Then what can you do? 3 phi of 1g here. Can you do anything to them? Remember that your codomain is a group of. So these elements are 3 group elements. Okay, so what can you do with them? There's a law. There's only one law you learn. Cancellation law. What does cancellation law do? You multiply what? Inverse to both sides. So what kind of inverse you can multiply? The inverse of phi 1g. Why? Does the inverse of phi 1g exist or not? Why? Because the codomain is a group. Every element should have an inverse. Okay, so by cancellation law or a more down to earth argument is multiplying phi 1g inverse on both sides. Okay, what do we get? So phi inverse 1g is, maybe use the other. Okay. Times phi of 1g times 2 phi of 1g. Right. Okay, so what do you get? On one side, you get what? The identity. But this identity in which space? In the domain or codomain? Codomain, right? Okay, because we map phi across already. Map the element across by phi. So we have g prime here is equals to, what do we left on the other side? We only left with 1 phi 1g. Okay, so we send an element in group to an identity in the codomain to the identity in the I send an identity element in the domain to the identity in the codomain. Okay, does it make sense? Okay, so one skill I use here is I use the property of identity. Make sure you know how to do this, we can create stuff. Okay, create two things from one thing. And this is very special, very special, so you need to remember. Create one from two. Usually it's impossible. You need 2 persons to build a baby. But now 1 person can build a baby. Yes. Okay. Very special this guy. Okay. Next thing. So what do we want to do for the next one? Okay. So what do we want to show? So I want to show that for every A in G, we have what? P of A inverse is equals to PA inverse. Okay. So any idea? Any idea on how to show this? So one skill that you need to have to do this kind of math proving question, right? Actually, I would say that you guys are lucky. Why would say that you guys are lucky? Because the knowledge you learn now has a textbook. The knowledge that we do research, there's no textbook. Not even there's no textbook. There's no one know about the topic we are researching. So why I say this is you are lucky, because I tell you what is true already. So this is a hint for you to prove stuff. So you should start with this hint. Don't go and find other stuff. Just look at this hint here. Can you play around with this hint? Answer is already given to you. So work backward. And so this is one skill. You can work backward. Can you work backward? Work backward. Work from the solution. And what can you do here if you work backward? So let's do working first. Then let's do a backward working. So what can you do if you know that this is true? What can you play around? Can you play around with this equation here? Can you play around with it or not? Can play? Inverse. How you play with inverse? BA, right? So you can try play around. Okay, maybe different people have different play style, but let's do this. So what if we do this? What happened? What do we get? On one side, we get what? Identity on G or G prime? G prime, right? Because it is a composition at codomain. How about the other side? You can combine, right? This is a group homomorphism. So you can combine. So group homomorphism allows you to combine, split, and combine, split. Then you can either choose which way is easier. But what is this? This is 1G. But this is 1G. But isn't it this is what we proven just now? Okay. But everything here can go backward and forward, right? So we have proven the last thing and then we can go upward. Okay, so where should we start now? Can you tell me where I start? Not that. We know, from B, we know what? P of 1G is equals to 1G prime. Then let's take an arbitrary element in G. Then what? Then phi of A inverse.
it doesn't matter if I choose any direction. I think it doesn't matter. Is what? Is 1G prime. Okay, but what? But phi is a homomorphism. Okay, so phi of A times phi of A inverse is 1G prime. Then again, you use cancellation law or multiply phi A inverse on both sides. Then multiplying phi A inverse on both sides, we get what? We simply get phi A inverse equals to phi A holding inverse. Okay, this is what we want to show. Does it make sense? So the only thing here, we use property of identity using the property of inverse and then using a property of group homomorphism. That's all. Does it make sense? Okay. And there's one question I want to ask you. I saw all of you like imitating me using QED here. Is this your old practice or you just started in this course? This course, wow. Seems like I managed to convert you guys to use this QED. Yeah. But anyway, this QED is the Latin word used by very classical mathematician when they do these exercises. Just normal exercises, they will put QED. And there's actually other stuff. Maybe it's QEO or QEI, something like that. Yeah, Newton will use this thing. Anyway, yeah. Okay. So before we finish, not finish, break, before we take a break, how about we introduce a few more things, then we will continue next hour. So speaking of this group homomorphism, right? So we know that group homomorphism. Actually, usually people won't say homomorphism. People will say morphism. I don't know if it's people or just US people, because I was taught by US lecturer. So they will say, sometimes they will just say group morphism or morphism. Okay, no homo. Huh? No homo. But I put a short form homo. But anyway, so these refer to the same thing. So in this class, they will be the same thing. Okay, homo or morphism or homomorphism, they are the same thing. Okay, there's no ambiguity here. So remind you that this group morphism is a map. So do you know any language about map or not, or function? Whenever you talk about function, what thing you learn? Sorry? What language? I mean, when you talk about function, what's the natural thing you study? Sorry? Calculus? No, not calculus. Some mathematical object. If you have a function, composite function, okay, yeah. Domain, codomain, anything else? Objective, not yet. Before that, linearity, that one just refers to specific function. But for general function, what do you have? If you map a point across, what's that thing? Sorry? One-to-one. That one is a property of function. What object you get? Yeah, image. Image of an element under this function. And then you can also look at the pre-image. Okay or not? Yes, good. So I'm gonna recall those things for you now. Okay, so let's imagine a picture first. I don't want to put too many words. Later you just look at word. You forgot what I say. You cannot imagine what I say. So let's draw our two groups. Okay, like this. So it's not, I don't simply draw these spaces because in advanced maths, we really think of group as some spaces. Some spaces will have a group property. Okay. So so what's the first thing I want you to know is how about so if you have a function, right, what you typically do, you should tell me where all the elements in the domain go. Okay, so you typically will map this phi here into a image set. So let's call this an image set. Let's say, how do we call it? What's the sensible thing to write here? Okay, I want to teach you what sense. What's a sensible thing to write here? You have phi apply on G. You will write phi G. Okay, what's this phi G here? Phi G is the image of G. Okay, under the map phi. But how do we define this? Okay, this is a very important thing. So how do we define this? So let me make a different color here. Yeah, okay, this. So what's this phi G here get defined? What can you think of it? It's defined by what? All the element, how about use Y? All the element in G prime such that what? Such that Y equals to phi of something inside your G. Does it make sense or not? That's the image. Okay, so this the English I also need to write it for you. So this is called the image. Image of what? Image of G under phi. Okay, image of G under phi. Okay, so image means what? The element inside here that's coming from G sent by this phi. So you can think of this phi as a spaceship. 一个火箭还是一个飞行器 ，OK， 把 G 的 element 带到 G prime， 可能从地球带到月球 ，OK， 从地球来的我们才是叫 image of G， 看到 ？Does it make sense? Okay, if it's coming from the domain, okay, sending by the map phi, we call it an image of phi. Okay, so you can see that I can replace this GS with any subset of G. Does it make sense? I can replace this G with any subset of G. Okay, so this is called the image of G under the map phi. Okay, so this is image. The other thing is about pre-image. Okay, so the other thing is about pre-image here. So, for example, I can look at this one particular phi prime here. Okay, what's the possibility to have elements from G to Y prime? Okay, first of all, there must exist at least one guy that gets sent to Y prime. Can I do other things or not? Can any other thing get mapped into this guy? You can. Okay, you can. Because why? This doesn't violate the definition of map. Correct or not? What's a function? Very important. Definition of a function is very important. So what's the definition of function? For every element in the domain, you need to associate a unique element in Y. But it doesn't restrict this kind of property. Why? It doesn't prohibit this kind of behavior. Why? Because you still what? You still follow the rules. One element in the domain gets sent to one element in the codomain. Take that rules. How to violate the rules that says one element in the domain has to go to a unique element in the codomain. If you're trying to define X go to Y prime and then X go to other thing Y prime prime, then this cannot happen. One thing cannot go to many things. Okay. So it cannot be one to many. It can be one to one or many to one. And also cannot many to many. Okay. So one cannot have too many
wives or husband. But that's not true for some religious, right? Okay, never mind. Okay. Right. So make sure one go to one element in the domain go to a unique one. So one last thing we introduce and then we'll take a break. So if you collect all these x and x prime, right? So we will define that. So let's do this. So phi inverse. So let me use that color. Phi inverse of, let's say, y prime is all the element inside G such that what? Such that if you map x across, it is equal to y prime. Okay, so this is called what? This is called the sometimes you'll see pre-image, okay, or inverse image. Okay, inverse image of y prime. Okay. Can you imagine or not? Image, okay, image sending to the codomain. Pre-image then, so pre or before the image, okay, so you go back to the domain, pre-image. Or inverse, you're taking inverse. So I want to remind you or warn you here, this inverse here is what? It's not a function, no? Okay, it's not a function that when you do phi inverse phi equals to identity. This inverse here is defined by this set. Okay, I want to remind you here, warn you, this inverse here is a set, not the inverse function. Does it make sense? Okay, this is a set. Okay, so whenever you see phi inverse, you should ask yourself, is this a inverse image or inverse function? This is two different things. One is set, one is function. Does it make sense? Set and function is different. Okay. So inverse image, remember this definition. If you don't understand what I say, I just want to warn you that remember this definition first. Later you will discover why they are different. Must remember this definition. It's not the inverse function. When you compose, you get identity. But they are related. They are related. How about talk one more thing and then we finish? So what if this image is equal to G prime? You know? If this image, you imagine this blue circle here grow until the whole G, what happens? Meaning you can map to every guy in the codomain. There's a special property we call, right, for this kind of function. Surjective or onto. Onto, right, because you can hit everyone inside the codomain. You can hit onto or surjective. The other thing is about this pre-image here. What if this pre-image is very loyal? Meaning what? There's only one unique X inside here for each element in the image. What happened? Then we say that this function is injective. It's one-to-one. Okay. Later we will introduce again. We will talk about it again. Okay, any questions? No? So these are the very important thing you need to know whenever you have map. Is this in chapter 0 already? Okay, please include this in. This is a very general property for injective function, surjective function, and then image, pre-image stuff. Okay. Please take note. Okay, let's break until 6:08. Hey,
它是 object 嘛，
所以是
image，
是 set of 东西哦。
对，它不是 object，
object 指什么呢？
因为它不是之前不是我们都是用 object 去 image 的，
比如说，
不是那个
哦，哪一个我不知道，不确定。
就讲讲它那个
function 也算 object 对我们来说 ，mathematical object 还是你 object 是特别的东西 element 哦，对。但是你要小心哦，我们在不同世界的 element 可以是 function， 也可以是 matrix， 也可以是，所以要比较准一点。Yeah。
But 我现在要区分的就是这个是一个 set of， 你也可以说 set of group element，but function 是不同的东西。function 我要告诉你东西哪里送去哪里，东西哪里送去哪里，但是这个只是一个 set of 东西。set of function 的差别就是 function 要告诉你什么送去什么，但是我现在没有告诉你什么送去什么，我是跟你说有一组东西。
set 跟 function 有什么差别哦？
啊，
来，我看。
我不该讲完的。
我想到
你不点我？
你要点，
就
你点一点我就不能认识你班了哦。等下我点一下，等下我点啊。
我先收拾。我发现还是错的是我的确是在这个。
它是一个名词。
同样我的也是 n， 同样也是 n smallest positive， 我这就是 order A B order P， 所以我是我觉得要扣到到 B，
对，没错没错，
order B，
没有错，
它肯定是小过的。
呀对，
所以 similar
呀可以了，
可以这样就可以
这样就是这样，就是这样，因为你找到它变成一，但是不一样的号码嘛，但是它是最小的那个嘛，最小那个就要小于那个半的。
所以我然后因为我已经说到 BA 是 order BA 是小过的 order A， 可是同样我就可以说
没有错 ，M 小于等于 n 小于等于 m q n 等于 m，
所以是没有绑在里面。
没有，你觉得有吧？
我不知道，我有点怀疑。
为什么你怀疑自己？为什么怀疑？哎，这个很重要啊，怀疑自己是很重要。所以为什么怀疑？
我是很严谨的。
你觉得哪一部会？我感觉挺严谨啊。你觉得哪一部？然后我们可以讨论。Yeah。OK 吗？
可是这个只能不到它只是finite的世界是这样，人在 finite 的时候啊。
infinite 啊，我想一下啊 ，infinite 啊，可能你用 contradiction
我觉得就是
suppose 这个是 finite 的，then 就会 contradict 另外一个情况。
其实我在想，
可以啊，
每条图案一个表示不同的，
不是重要，可以啦，不能先。
不要从同样的开始写，不是谁。
没有，如果真的它两个要infinite嘛，那你就 suppose 其中一个，
就是人类的
脑洞大
contradiction 嘛 ，suppose set of set of contradiction。如果不是 infinite，肯定就是要 finite，没有其他选择了啊。等你就用你的方法又推得出，它提早等于这样提早那个又大于infinite。但是呢，你注意哦，我的 definition 好像没有 infinite 这个 case，
不需要 proof。
现在我们打
其实可以 include infinity 啊，比如说 if I cannot find the smallest infinite subject，then 我就 by convention
就规定它的 order 叫 infinity。
对。
而且现在我本来打完了，但是刚刚张鑫一直在问我问题，所以我没来得及帮你打完。
一个人。不用。
关于我说的一个
这个是比较强的，这个去这个就一个方。你会不会记哦？
对，我知道你是怎么我说那个题目。他是这个啊。我看到这个 support 这个东西，因为假设哦，你 support 这个东西永远是那个单的，所以如果你要保这个方式，那我是方便讲说。然后一个 example 是那个里面会有这种，不是长，一想，这个。OK， 就是说，你看你这个 contradiction 是需要这一步成立。如果这个世界里面这步不成立的话，会不会很好？就是说，你可以找两个方法，会就是可以找两个方法，就是庞小杨 ，OK， 林宏杰，宏杰，还定在说宏杰 ，OK， 子明呀，子航 ，OK， 子航 ，OK，Adrian， 嘉玲，子轩，伊莲，嘉玲 ，Doki，Eugene，Jasmine，Albert， 陈碧，陈碧，我记住一下你们的脸啊，英语。Free， 好，戴一成，心仪，优彤，冰夏，冰夏，哦，OK，sorry，皎月，皎月 ，OK， 子涵，哦，对，子涵 ，OK， 洪瑞友，宇轩，哦，宇轩 ，OK， 嘉怡，方瑜，方瑜 ，OK， 嘉怡，朱瑶，云溪，汤云，颜色，姚一成 ，OK， 对 ，Eric， 一凡 ，OK， 钟一凡，安平的 Rosin 的赵胜的 Manchun 的昊天的金星 ，OK， 金星，一行呢？哦，又係一行，肖這個 Rachel 個 Rachel 個唐星林 N 個 Ian，I think I saw Ian， 郑月個赵瑞個金鹏 ，OK， 金鵬，韦澤林金個，林金個。Hello, testing. Okay, so let's continue with our group homomorphism here. Right, so there's more property to come here, so let's do it. So let's be from G to G prime be a morphism. Okay, be a morphism. So there are two things to see here. If, okay, H is a subgroup of G, then if you look at the image, okay, the image of H, what do you get? What do you expect? In abstract algebra, we value symmetry. Do you know what symmetry means? 中文是对称性啊，就是说左边跟右边应该要一样，或上面跟下面要一样，or anything symmetry. Okay. If you see there's a subgroup property on the left, what should you expect? You should expect some subgroup property also happening there. But if you want to talk about hash, phi hash as a subgroup of what to make sense? Of G or G prime? G prime, right? Because when you map across, you stay inside the core domain. Okay. Another thing is you can go backward. Actually, you can go backward. If you have a subgroup in the core domain, what can you look at? Okay. We have a spaceship go from domain to core domain. We have another spaceship to go back. What's the other spaceship? How to go backward just now? We can take the inverse image. Okay, not inverse function, inverse image. We start with image first. Inverse image. So you can look at all the set that gets sense that has image in K prime. Okay. So this is a subgroup of what? G or G prime? G, right? Because you go back to the Earth already. Go to your hometown. Okay, good. Good. So, okay, we will just prove one statement here. The other I left for exercise. So let's do one. It's a similar proof for the other one. So let's do one first. So very easy. Okay, very easy. Why is it easy? What do you want to show here? You simply want to show that of H is a subgroup. So what is the three property you need to show so that you can show that something is a subgroup? Seng. What's the three things you need to show something is a subgroup? Closure, identity exists, and then inverses exist or okay. So what does closure means? You need to take how many things? Two things, okay, inside your set, and then show that the product is inside the same set. Okay. So I mean, algebraic proof is very easy. Okay, depend on comparing to analysis, because what we do in algebra is we unravel all the definition. Okay, but if you look at analysis proof, you need to construct. Let A be what set? Want to find epsilon? Want to find delta? But algebraic proof is usually just unravel the definition, then you can see the property already. Okay, so what do I mean by that? So if you want to show for a universal quantifier object, right? So you just simply take any arbitrary two elements. Okay. But what does it mean by A and B is in phi H? What does it mean by that? Meaning what? Meaningful? Meaning what? By definition, what does it mean? So the image of something. Okay, so this is very how to say mnemonic, so very symbolic. This is inside a set look like this. So this means what? Meaning there exists X and Y in H such that A equals to Bx and then B equals to By. Okay. So remember, this is what? This is what? This is a set. So what set is this? Image of H under P. Okay or not? Okay. Yeah. So it comes from someone inside H. Okay, come from someone inside H. But why I want to do this? Do you understand? Why do I want to do this? Why do I want to do this? What's the goal here? Look at the goal. Every time you forget, every time you run, you confuse. You should do what? Go back and think about what your goal is. Every time you lost run, go and find your goal. Okay? Go back and find your goal. If you lost, go back and find your goal. Okay or not, Seng? Don't find me, find go on. Find goal first. Okay, find your goal first. So, what's your goal? You want to show that A times B is in the image of F, meaning what? You can write AB as a P of something. P of something. And let's see how we achieve this. So we know more about AB now. Okay. So then what is A dot B in this case? It's just phi x times phi. What can we do with phi? Homomorphism. So we can combine phi x and phi y. So what? So what did we find? We have write the product of AB equals to P of something inside H. Is it something inside H? Why? Why X, Y have to be H? Because H is a subgroup. S is in H, Y is in H. The product of X, Y is in H because H is closed. Does that make sense? Okay. So I would say since X dot Y is in H, as H is closed, so we have write AB as an image of XY. So we have A dot B is in phi of H. Okay, no? Okay. Yeah. Right. How about identity? How about identity here? We want to show here. We want to show what? Lost again. Ayo, Pan Seng, you lost 了。怎么办？ Q 一下你才会听课。来 ，What do you want to show? What identity? This identity has to live at where? Who has to have the identity? Okay, 你看是不是 So what's our goal here? What's our goal? We want to show that phi H is a subgroup. So I need to prove that this phi H has a identity. Okay. So what do we want to show here? We want to show that the identity in the domain, in the codomain is inside phi H. Is it true or not? Huh? Is it true or not? So can you write? So okay, again, translate this question. So if you want to show that it is an image of something in H, meaning what? You want to write IG prime equals to phi of something in H. So what's that thing in H? Huh? What's the thing in H? Identity in where? Seng's what? Seng phi of IG equals to IG prime. We have IG prime is in pH. Okay or not? Because we write IG prime as an image of something inside H. Is it clear that why IG is in H or not? Is it clear that why IG is in H? Why? H is a subgroup. Okay. Maybe you'll be more pedantic. Why does the subgroup identity have to be equal to the identity in the original group? So meaning maybe you can ask why IH is equals to IG. You can prove it actually. Okay, you can prove it within the group. Okay. If you get a subgroup, the identity inside the subgroup should be the same as the identity inside. You can prove this. Okay, you can prove this. Otherwise, you can assume that IG is inside. It's the same identity inside your H. Okay, so everyone agree with this? Any question? No question? This is what we have proven. And then IG is in. So maybe if I want to add a few more words, I would say that N IG is in H because H is a subgroup. Okay, so we are keep using that we have a subgroup, and then we have a homomorphism. Correct or not? Here, the second property here is a subgroup property. The first property there is a morphism property that we proven just now. Okay, sending identity to identity. Okay, combine them together, we have a new result. Does it make sense? Question? Hi, Jialing. Got question or not? A bit blur. Question? Ask. It's okay. Just ask. Maybe your question is others' question. No question? Okay, you can tell her. Others got question or not? Any question? Feel free to ask. What's that? Why cannot have one? Good question. Where does 1G prime live? Where does 1G prime live? G prime is domain or codomain? Codomain, right? Phi map from where to where? Domain to codomain. Yeah. So if you do the other way around, it's a different map already. Does it make sense? Yeah. Your spaceship only go one direction. The other direction need the other map. Any other question? Hey, this kind of question is very important because this is a little small thing that confuse you. Okay? If you remove this confusion, then you are as pro as me already. Seriously. So life is about removing confusion. And remove as many confusion as you can. Okay. Okay. Right. Any other question? Okay. Okay. So how about the next thing? So inverses. How about inverses? So what do you want to show? Like Pansing. What do you want to show? No, Pansing first. If you correct in the stroke of 3, then I will stop asking you. 我这样怕咩？做不用紧的，来试试。How to prove inverse? What do you need to show? Say. 什么 inverse 在 G 派里面？ H is a subgroup. There's no inverse of a subgroup, right? So you want to show what? What's your goal? Confused, what's your goal again? You want to show that phi H is a subgroup. Meaning what? Every element inside this phi H has an inverse. Okay, so we want to show that for all, let's say we call it A prime here, in phi H, there exists a what? There exists a P prime. So meaning what? This kind of proof is what? Is the existential proof. Existential proof means what? You need to find me one. Okay, you need to find me one. Hey, sorry, a bit confusing. So a typo here. So you need to find me one candidate for A prime inverse here. How to find? No, I tell you, this is an algebraic proof. So algebraic proof, you need to unravel all these definitions first. Unravel first. So meaning, what does it mean by it is inside this image? What does it mean by it is inside this image? Write it down first. Okay, if you write every definition down in algebra, most probably you will see the rock already. No need to construct much. Okay, let's see. Let's try. So let's start with an arbitrary A prime first. Okay, because we need to show for all A prime, right? So let's fix one. Hey, salah lagi. Sorry. Because in my note, I use different phi. Both of them are phi. Okay, so what do we do here? What do we do here? What do we do here? What should we do here? Note that this set here is live in where? This set live in G prime. This element, I mean. This element live in G prime. Meaning what? Actually, there exists a prime inverse inside G prime already. Okay, but how is it an image of something in H? Okay, how do you make sure that it gets sent from someone in H? Okay, so now we are left to show what? We are left to show A prime inverse equals to phi of some, let's say W, for some W in H. Okay, so you see 我们这个目标不会，我们就换另外一个目标。Okay, so we first want to find an inverse in pH, but now we turn to find some element in H, such that what? Such that PW equals to this element. Okay, so we change our goal already. This one can also change a smaller goal. And see if we can achieve this one. So let's see what games we can play here. Any idea what games we want to play? Can play? We haven't really used another assumption, right? What's one assumption we had? Yeah, not yet. We still have one assumption we can play first. So we fix what? A prime is in pH. So we can write A prime as a form of phi of something. Okay, so we can do that first. So note that there exists, let's call it what? Call it Z, such that such that A prime equals to phi Z. Okay. So, any idea or not? No idea, huh? What can you play? Huh? So Dala means what? Move who? Sorry? So I mean, okay, what's the difference between this A prime and this A prime? You got the inverse here, right? So if you imagine you have this already, then you can take inverse. If you take inverse, here is what? Phi Z inverse. But just now we say there's a homomorphism. If it is a homomorphism, we can break that in. So maybe we can try that. Okay, let's try that. Yeah, let's try that. So how about choose W to be Z inverse? Okay, see, try first. Experiment. Mathematics, you need to do experiment. Yeah, that's the experience you need to do. Okay, do experiment. So how if we do this? What do we need to check? We just need to check whether phi of this thing is phi of this thing is what? Is A prime inverse or not? Okay. So choose this, then what? Then phi of Z inverse is what? Is phi of Z everything inverse, which is what? Which is A prime. Why? Because we use the homo property. Okay. So we have found the required W now. We found required W now. Fine. Any question? 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 you need to know what you want first. Okay, you want to know what you want. Okay, you need to know what you want. Any question? Yes. Thanks, well. Thanks, what? Line CH. Because we found because being in the VH means what? There's a element in the H such that you map it across. It equals to the equal to the image. Does it make sense? What are you asking? What's your question again? Which one? This one. This one not necessary in what? Not necessary in H. Is it necessary in H or not? So Z is in sorry, I think I do some stupid thing here. So so it's not just in G, right? It is actually in H, right? Because A prime is in the image of H. Okay, but when we define this Z inverse here, does it necessary in H or not? Because H is a subgroup. Okay. Things H. Yeah. So we have written what did we do here? We have written the inverse of A prime as a image of something inside the subgroup H. Okay. Hey, there's a very I think one thing you were confused about this proof is you need to understand that as this W have two kinds of reading here. One is assume, one is proof. There's two ways to read. If you get rid of this, there's two ways to read that exists a W meaning. Okay. If we assume there exists a W meaning what? We have W. If we want to prove there exists a W meaning what? We want to find W. Okay, so there's two ways to read a statement with that exists. Okay, if you read it only with one way, you will confuse because you don't know what you have and you don't know what you want. Does it make sense? Okay. Yeah, you need to get used to it. Okay. Does it make sense? Okay. Okay. So every time you confuse, remember what do you need to find? Find what? Every time you confuse, what do you need to find? Find your goal. Okay. If you want to achieve your goal, you need to look at what you have. So these two things very important. What you have, what you want to achieve. What you want to have, what you want to achieve. If you forgot, ask again. What is your goal? And then what you have. Okay, two things. Assumption and target. Assumption and target. Okay, you need to differentiate between these two things. All right. So let's continue. Any other question about the proof just now? Feel free to ask. Don't look at me, just ask. Don't look at me. 没有什么好看我看你的，就问吧。Okay. We just want to proceed. Okay. Remove all your doubt and my doubt. All our doubt must be removed. There's one word that Hubert says. You know who is Hubert? David Hubert. We must know and we will know. Who is David Hubert? David Hilbert is a very famous modern mathematician. He come up with yes 23 very important monumental question in mathematics, and then they are being solved already actually. But Hilbert is a very established mathematician, and then he involved in a lot of various field of mathematics, even physics. Okay. I think they say if Einstein hadn't found relativity, maybe Hilbert would find it. They are living in the same era. Area maybe overlap, but era. Same era. Same about the same time. Era. ERA. Yeah. They are the same, I think, maybe. I don't know, it's colleague or enemy, I don't know. But I mean, they work in overlapping field. Okay? Yeah, we must know and we will know. Okay. Understand or not? Understand this word or not? 我要知道，我会知道，我将要知道。Yeah, the problem is this one. Okay. Yeah, so we have to know. Okay. Okay, any question? No? Okay, then we proceed. So we will leave the second proof as your homework. I will provide solution. Please try use the similar argument, unravel the definition, and then you prove the subgroup property. So the second statement says what? If you start with a subgroup inside your codomain, if you look at the pre-image, and then that pre-image will form a subgroup. Okay. So meaning what? If you look at these two statements, says what? If you have what? So you need to able to turn this into picture. So in this class, although I put a lot of algebra here, actually it's quite geometric. So if you have two groups here, okay, and then you consider subgroup inside G, if you have a homomorphism, you map this across. If you look at the image of this phi, it is still a subgroup. Okay, so meaning what? You send subgroup to subgroup. Okay, second statement says what? If you start with a subgroup inside your codomain, let's call it K, you go backward. Okay, you go backward by what? Not spaceship. You just look at who gets sent to this K here. Okay, you look at the pre-image. So pre-image, how to draw? Let's draw one line here. So you look at the pre-image. Okay, pre-image. So phi inverse of K. So it's again a set. But this set is nice also. It is also subgroup. Okay. Yeah. Coming backward is not by spaceship. I just look at who gets sent to K. Okay. And my spaceship only go forward now. Okay, I haven't go backward yet. Only go forward. Okay, pre-image are looking for all the passenger get sent from the domain. Again, form a subgroup. Okay, so there's a correspondence between these images and pre-image. Does it make sense? Okay. Okay. So this is a picture you need to remember in your brain, and then you need to know how to prove it. Okay. First, understand the statement first, and then talk about how to prove. If you don't understand the statement, don't bother to prove it. You won't do it. You won't be able to do it. You must understand statement first. Okay, statement very important. Okay. Right. So let's define a few stuff before we go forward. So how is it to be a homomorphism to be surjective? Okay. So a group homomorphism, P, G prime, is surjective if what? Or onto? If the image of the domain is equals to the whole codomain. Okay. In other words means what? For every element inside your codomain, there exists some x in your domain such that what? Px equals to y. Okay. So all of you are coming from G somehow. Second definition about injectivity. So I just blah, 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 blah. Phi of G to G prime is injective. Okay, so let's label this. So surjective onto is a adjective or nouns? Adjective, so meaning it attached to a nouns. So what nouns is it? It's a homomorphism. Okay, so we define surjective and injective on homomorphism. Actually, in general, we can define it for a function. Okay, because group homomorphism is a function, so we can define on it. So injective and one-to-one means what? We will take a functional definition here. If what? If phi, so if phi x equals to phi y, meaning what? Meaning it must come from the same guy. Okay. There's another equivalent definition, but we will take this as definition for our class. Wait, let me see. Okay, good. So next, so later we will see how this property get related to our homomorphism, the different object in our homomorphism. So we have looked at image, pre-image. Okay, there's another thing we want to define here. I think you see this before. It's called the kernel of the map. Kernel of a map. You know what the kernel of a map is? Yes. Yeah, right. Noun space. What does noun space do? What does noun space do? Good. But the zero in our case is what? Identity element. Okay, so the kernel of a map is the set of elements in where? In the domain or in the codomain? In the domain, such that it get maps to the identity in the codomain. Okay, you will think that yeah, so many words here. So we should be able to write it down in a mathematical symbol. So how do we write it down as a mathematical symbol? So that's why I asked you whether something is a set or a function. So if it is a set, you should be able to write it in a set form. So what's this set form here? These are all the elements in G such that what? Phi on this element, you will get the identity in the codomain. Anyone think about where this kernel word coming from? Okay, linear, you are sure. But the kernel in English is what? Like walnut. Walnut is a kernel. You know, before you eat the walnut, you need to break the nut first. Do you know? You know, before you see the walnut, there's a shell, which we call the nut. Okay, so kernel is living inside the nut. What does nut look like? It's like circle. Circle looks like what? Zero? So something gets sense to zero. Kernel, we call it kernel. And it's very make sense one. Mathematicians don't simply pick terminology one. It's very, very make sense one. Yeah, okay. So this kernel you get sent into nut, the identity. We abstract it now. Okay, so one nice thing about this this kernel is we can prove that actually this kernel is a. And now this kernel should be a subset, right? But in our subject, when we look at a subset, we want the subset to be what? Subgroup. So we want to prove that this kernel is actually form a subgroup. Okay. Yeah. So now I'm trying to build your intuition. Whenever we look at a subset of a group, we typically want to study whether it is a subgroup. So let's prove this. I think after proving this, and then I give some example, and then we can finish. So, 3 conditions to verify, right? Okay, now ask Jialing. Jialing, the middle Jialing, the yellow Jialing. So what do you need to check if a kernel is a subgroup or not? Oh, identity inverse closure. Okay, good. Identity inverse and closure. Good. Okay, so what kind of identity live inside this kernel? IG or IG prime? IG, right? Because this kernel is a subset of G. So we want to show that IG live in kernel of V. But what does it mean by IG living in kernel of V? Look at the definition. Does Phi of IG equal to IG prime or not? 1G prime. Why? Because Phi is a homomorphism. Okay, so we see that 1G live in the kernel of V since what? Phi of 1G equals to 1G prime as Phi is homomorphism. Inverses, Inverses, what do you need to show? For every element inside this kernel of Phi, we want to show what? A inverse also live inside the kernel of Phi. Okay. So what do you want to evaluate to? So let's see. So in other words, that is Phi of A inverse is equals to 1G prime. But what did you know? Not that. What is phi of A inverse? Equals to what? Phi of A, everything inverse. Because it is a homomorphism. You can commute the inverse operation. Okay. Since phi is homo. Then, what do you know? What is phi A? Phi A is what? Yes, phi A is IG or IG prime. IG prime. Okay. Because A is in the kernel of phi. But what's the inverse of identity? It is itself. Yeah? Okay. How about closure? So you need to take any two elements inside your set and then show that A dot B is in kernel of B. Okay. So right. So here, I mean, let's do here since let's fill this gap since A is in the kernel of phi by assumption. Right. So we need to verify that AB is in kernel of phi. Okay, but so what is phi AB in this case? Not that phi AB is what? Phi A times PB. But what is phi A times PB? Is again identity because by what? By assumption. Okay. But what is phi A times what is IG times IG here? Is just IG. So it is in the so it form a group. Okay, does it make sense? Any question? Question? Is it clear? Okay, so what we do here is just using new definition and then plus some group homomorphism and then plus some more. That's all. Yeah, group homomorphism. Okay, let's look at some example and then we will finish. So what sort of interesting kernel you have looked at? Okay, what sort of interesting kernel you have looked at? We have looked at few homomorphism, right? I gave you quite a lot last time. So we can look at all the kernel, okay? All the kernel of those homomorphism. So in particular one, there's a map from the GLNR to where? To R cross. Right or not? So if you so these two are group, right? Do you agree? These two are group. Set of invertible matrix form a group, and then non-zero real number form a group under multiplication. Okay. Hey, actually, we can give this R across another name, GL1R. Okay, invertible real number. Real number has inverse. Okay, GL1R. So we make it formalize. So what's the kernel of this thing? Where does this kernel live? Kernel is a set of elements in the domain or codomain. Domain, huh? But the domain here is what? Matrices. So these are the, so what's the identity here? 1. So meaning what? The kernel of this determiner is what? Is what we call the SLNR. Why? How we define SLNR? These are the all matrices in GLNR such that determinant of M is equal to 1. Okay. Sorry. I define here. So this is how we define SLNR. This is what we call the special linear group. Okay. This is how we define it. Okay. Okay or not? Last time I showed you that this group form a subgroup, right? Why? Determinant of AB is equals to determinant A times determinant B. So if AB has determinant 1, determinant of AB also have determinant 1. Okay, form a subgroup. Correct or not? Just now we proved that kernel form a subgroup, right? It's a subgroup. But this equality here, whenever you want to check equality here, right? There's 2 things to check. You have to show 2 subset inclusion. Okay, to be formal. Okay, next. How about the homomorphism, the sign homomorphism from Sn to the group of plus minus 1. Hey, how plus minus 1 form a group? Can you imagine? What sort of LLC you can put such that these 2 elements form a group? Multiplication. Can you imagine? 1 plus 1, 1 times minus, 1 times 1, 1 times minus 1, minus 1 times 1, minus 1 times minus 1. Okay, so let me put my multiplication here. So what's the kernel? What's the kernel of this map here? Is an element in Sn such that it gets sent to the identity. What's the identity on the other side? 1. So what permutation has sign 1? All the even permutation, which we call the alternating group. And these are all the even permutation. Okay, so this is called the alternating group. Okay, last time we also give this alternating group as a subgroup of Sn. It turns out to be a kernel, okay, of some homomorphism. What else we can look at? How about the kernel of this exponential morphism here? Let's do R to R star. Okay, so the first R, what's the group here? We just do plus here. Okay, and then we send it to a multiplicative. So what's the kernel here? What's the kernel here? So if you want to ask about kernel, what's the identity in the other side? 1. So E of what is 1? Only 0, right? Okay, so this is a singleton set 0. Okay. Obviously, you need to show 2 inclusion. Okay, so 1 inclusion is clear. If you put E to the 0, you get 1. But how about the other one? Okay. Actually, you require that E is injective. Okay, anyway, so let's continue first. Let's talk about different stuff first. So, okay, so how about this kernel here? Kernel of this determinant, not determinant, the length function or the modulus on the complex number. What's the kernel here? What's the kernel here? Who has radius? Who has length 1? Yes, the unit circle. Okay, so it's the unit circle.
There's the unit circle. Okay. One last thing. One last one. Okay, before we leave, one last one. I want to talk about this. I want to promote algebraic topology. So remember this map here. What did we do? I think it's not U, it's S1. So we take the R, right? Then we wrap around the circle infinitely many times. So what's the kernel here? What's the kernel here? So to ask about kernel here, you need to ask about what's the identity in this space here. So what's the identity in this space here? 1 is the same as what we have last time. So when did you evaluate to 1 here? Just 0 is the whole Z. Multiple of Z will get this guy to 1 always. This guy is periodic in Z. Periodic in 1. Period is 1. Okay. So this thing is equal to Z. So you could imagine that what is e to the 2 pi I times 2 times 3 times 4 times minus 2 times minus 1 and so on. Whole Z. Okay? Yeah. So, right. So you can imagine if you go from 0 to 1, you will have a full circle coming back. So kernel tells you when you come back to 1. So if you have 1, then you group 1 round. If you have 2, you group 2 round. And then 3, 4, 5, 6, 7, 8. How about negative? Meaning you wrap the other way around. Okay, there's 2 orientation on your circle. Okay, so one task I gave to you is try and show all these equality. Okay, why this is in the kernel, and then why the kernel only contains these points. Okay, try and show this inclusion. Why? Because this is equal as set. Okay, set equality, you need to show 2 directions. Okay. Okay, any question before we break? Finish? Any question we finish? So yeah, so assignment will be extended to next Wednesday, and then we will release the next assignment. You can look at it first. Okay, so see you next week. 在听什么？
那个减一那个什么一乘减一，然后减一乘一，然后什么？为什么是 even permutation 啊？那时候你讲1秒的时候我懂。